here we go. So the recording, I think, hold on a sec, the lab. So this is acid-based solutions lab. Okay, what you have here is a solution, and you have a magnifying glass. Okay, this is nothing but water in the beaker. So you have a 1 liter. You can see it's a 1 liter water basically. The reason it is 1 liter because it is easier to calculate the molarity of or the concentration of the solution. Okay, because 1 liter, you can easily express any quantity into molarity, and that is the concentration. All right, so it doesn't matter. You can work it out. So you can see the dissociation of the water. Yeah, that's the reaction. This is how water molecules dissociate into H3O plus and OH minus water ion. You can change the solutions. You can change. Right now the water is selected. You can also change it to strong acid. You can also change it to weak acid or strong base or weak base. Okay, you basically you change which solution you want from here. Right now it is just water. All right, this is view solutions. All right, and also guys, keep your chatting to minimum, because again I don't want to get everything get recorded into the recording. Yeah, so keep your typing to minimum. Only important questions should be asked here. Okay, once I'm done, I will answer all your questions at the end of the lab. Okay, not in the middle. All right, so here there are different parameters you can change. We can see the molecules in the watch glass. Okay, in the magnifying glass. Obviously you need a microscope to see molecules, and you need a very high quality electron microscope to actually see the molecules, and you won't see it like this, but this is animation, so we can do whatever we want. You can also select the water molecules, and you can see that there are lots of water molecules. Okay, these brown, you can see this gray particles. Yeah, these are all water molecules. Many water molecules. You can imagine there are like gazillion molecules are there. Okay, now of these, some molecules will dissociate, and this is how we write the dissociation reaction. Yeah, some molecules, water molecules will dissociate. Some of these gray molecules will become H3O plus, and so here we are saying in the equation there are only two molecules that dissociate into H3O minus, H3O plus and OH minus. Okay, Harish, if you have lost the connection, you can re-click on the link. Okay, or refresh your page. It should be okay. All right, so essentially we can see the water. We don't need to, yeah, because this is just creating a visual distraction, so we'll just take it out. Yeah, so we can see that everything else is water. Yeah, and there are two water molecules that have dissociated into H3O plus minus ions. Yeah, so you can see H3. This is again not balanced. We can see two H3O plus minus ions and two OH minus ions. Okay. You can also change the equilibrium concentration. For water, you can see how the molecules are dissociated, the concentration of dissociated and undissociated particles. Okay, so this is for the concentration of pure water. Yeah, or undissociated water. You can see this is the concentration of H3O plus ions. This is the concentration of OH minus ions, and obviously they are equal. Yeah, and so since H plus ions and OH minus ions are in equal concentration, it is a neutral solution. Yes. Now we can also check the pH using one of these measures. We're going to use for this one, we're going to use pH meter and pH paper, but you can also use conductivity. See if there are any ions in the solution. If there are ions, the bulb will glow. If not, then it won't. Okay, so you can select if you want a pH paper or if you want a conductivity. So if it's here is the thing. If you dip the electrodes into the water, you can see the water will not grow as dark. You can see there is a slight glow in the bulb, so it's glowing a little bit because there's very few ions. But if you take, let's say, a strong acid, then you can see how bright it is. Okay, so you can conduct the weak strong acid or strong base solution have many ions, and therefore there is going to have high conductivity. You can do that. Okay, but we're going to use just the pH meter and pH paper for this experiment. Okay, um, 1 second. Okay, so first thing we'll do is reset all. Alright, so when you reset all, it comes back to this page. Now we want to make sure that the solution is water. Okay, we want to make sure that these settings are as it is, the molecules are selected, but show solvent is not selected. It's not clickable. You need to clear your cache, Harish. Clear your browser's cache and then try it again. Okay, so we have this settings. Yeah, so we've selected molecules. We don't want to worry about equilibrium or anything like that. Yeah, now we see that very few molecules of water are dissociated. Yes, yeah, very small quantity of water molecules are dissociated. We also see that H plus and OH minus ions are in equal quantity. Yeah, and as a result then the solution is neutral. Is Harish here? Harish is still gone. Alright, so we expect this solution to be neutral. Clear? Yes, we should expect the solutions to be neutral. Yes. Alright, so we can try it, and you can see that it is a neutral solution. Yeah, we can check it with the pH paper. So you take the select pH paper and dip it into the water. Yeah, and when you match with one of these, you can see that it matches with the 7. Yeah, so yes, the solution is neutral simply because there are equal number of H plus and OH minus ion in the solution. Okay, we can hold on a second. Alright, so now let's click on equilibrium concentration. Yeah, and we see that what is the concentration of undissociated water in 1 liter of solution? 55.6 moles. Okay, that's a lot of water molecules that are still undissociated. Yes, 55.6 moles. So yeah, 1 mole is how much? Large number. Yes, Avogadro's number 6.023 into 10 to the power 23. That is the 1 mole. That many number of molecules are contained in 1 mole of water. You have 55.6 moles of water in there in 1 liter of solution, and that is a most of the molecules are still undissociated. How many molecules of H plus ions are there? Yeah, 1 into 10 to the power minus 7. That is a very small quantity. If you compare that with 55.6 moles, you have 1 into 10 to the power minus 7 moles of molecule that are dissociated. This is a fraction of a mole. Yes, this is not even a mole, it is a fraction of a mole. Very small quantity is dissociated. Okay, and furthermore, nothing is happening. I have Asmita double for some reason. Anika, Asmita, I have two Asmitas there. I don't I don't know. Kirti, are you able to connect? Okay, all right. Yeah, I think some of us are having problem with join me, so what I will do is see what are the solutions we have. For now, I think we'll go with the old method of screen share. Yeah, so I'll stop join me. Yeah, so I'll just stop the join me thing, and also um, all right. Hopefully there shouldn't be any issues now. Um, so we saw that basically these are the concentration of H plus ions and OH minus ions, and since they are equal, obviously this is a neutral solution. Yeah, so you can dip it and it doesn't change the color, so that's a neutral solution. Okay. um, Alright, so now let's do again, click on reset. Okay, we'll reset so it comes back to the landing page, and let's click on weak acid now. Alright, so again it's a weak acid solution. That means majority of it is going to be water. There are some H plus ions are going to be there, and that's what we need to see. Okay, so if we see at weak solution, so these are acid molecules. Yeah, these are acid molecules, and since it is a weak acid, the dissociation is not going to be very high. Okay, it's going to be small dissociation, and you can see that not all of these gray particles have been dissociated. Yeah, because you can see many of the gray particles. Yeah, and if they dissociate, they would give out blue particles, which is the conjugate base of the acid. Yeah, so this blue particle is a conjugate base of the Ha, and it would give out H plus ions with water. Okay, so that's going to be H3O plus ions. Okay, so you can see that very few particles have been dissociated, not many. All right, so so let's check the pH with the pH paper, pH meter, and you can see that the pH is 4.5. Yeah, that's weakly acidic solution. You can also check it with pH paper, and you can see it turns slightly darker in color, and you can see that it's basically between 4 and 5. Yeah, so it's about 4.5. So it gives you a ballpark number of how acidic the solution is. If you click on equilibrium concentration, you see that now again you can see the water concentration is still high, but the acid has dissociated into H and into conjugate base and H plus ions. Okay, so you see there is some concentration of OH minus ions and some concentration of OH minus ions. Now this is not hydroxide ion. These blue particle are not hydroxide ion. These are basic, but these are not it doesn't give any basicity to the solution. Okay, but since there is an excess of OH minus ions in the solution, we get an acidic solution. Okay, and that is the reason why we got the pH between 4 and 5. Okay, this is, so you can see that there is a clearly there is no hydroxide ion in this solution. Yes, if you see the molecules, you can there is no hydroxide ion. In practical there might be a little bit of hydroxide ion, but the concentration is going to be very, very low. Okay, so do you see that? Yes, H plus ion, this is a weakly acidic solution because there is some excess of H plus ions in this particular solution. Okay, much of the acid molecules are still undissociated. Yeah, it is not you can see that the undissociated H plus ions are still there. H8 is still there. Some of them have dissociated into this. Okay, if you yeah, so we'll talk about that later on, I guess. So let's go to a strong acid. So again, click reset, yeah, and click on strong acid. Okay, now you got a strong acid, which is again the same type of acid. You know, it's a gray acid, but do you see any gray particles in there? Remember that the concentration is still same. Okay, we are not changing the concentration, but we are changing the strength of the acid. There are no H plus HA ions in there. Okay, sorry, HA molecules, and there is no acid molecules in there. Why? Because it is a strong acid and it will dissociate completely. Okay, it will dissociate completely. You add, you know, more, you know, there is a limit to, as I said, there is a limit to how many molecules you can add and how many, but you know, under normal circumstances it will dissociate all the particles you add. Some particles are still going to be undissociated, but again it's going to be very little. Okay, so obviously you still don't have any hydroxide ion. Okay, so you have excess of H plus ion. So this should be there are many H plus ions as compared to weak acid, as compared to the previous case. Yes, and if you check it, it should be strongly acidic because just there are many H plus ions in this solution. Yeah, and there you go, it's a strongly acidic solution. You can check it with the pH paper and turns slightly reddish, and so you can see that it's about 1.5 and 2, something like that. Okay, you can click on equilibrium concentration here. Okay, so this is shows you the concentration of various species in this solution. Yeah, you can see that water molecules are still there because it's a solvent. Yeah, because the water molecule, you can see that even though water molecules are dissociating, correct, there are some water molecules that will turn into OH plus ions. Yes, H plus ions are combining with water molecules, so obviously H2O molecules are getting converted into H3O plus ions. Yeah, but do you see the change in the concentration of water as compared to previous two cases? You don't see any change in the concentration of water. Yes, in the amount of water is still the same. Why? Because it is such a large number that water is in always in huge excess. Okay, it does not change. You know, some molecules, you know, if I take 1 million molecules goes off and becomes water, it still doesn't change much for water. Yeah, it's still going to be a significantly large number of water molecules still going to be there. Okay, so it doesn't change. But what you see is now the acid molecules have completely dissociated, absolutely no water molecule. So it's negligible. Okay, it's almost, it may not be zero, but it's almost zero. You can neglect it. Okay, you don't have to worry about it as far as the concentration of the acid is concerned. Okay, but if you look at the concentration of conjugate base of that acid and H plus ions, you see that this is significantly high as compared to previous cases. Yes, and therefore, so let's compare with weak acid. This is weak acid, this 10 to the power minus 5. Okay, and this is strong acid, 10 to the power minus 2. This many times more than what you had for weak acid. Okay, so there is a magnitude difference between dissociation of weak acid and dissociation of strong acid. And so that is the reason why the pH for these strong acids are lower. Is that clear? Okay, so let's do the reset. Wow, that's a big yep, Asmita. Let's check with weak base now. Okay, all right, here's the weak base, and again this is the base molecules. B is the base, it's again gray. The solvent molecule is in bluish. Yeah, we don't have to worry about that, they are there large numbers. You can see how many water molecules, solvent molecules are there. Yeah, for so just to give you an idea, so it doesn't make any difference. It doesn't make any dent in the concentration of water molecule as far as the reactions go. Water is always going to be in excess. The reason I'm saying this because many people find it difficult just to digest the fact that how don't water molecule don't change. Okay, and this is, I'm talking about your senior batch. They will have, and so when you go to the 11, you will deal with this in equilibrium concentrations. Yeah, and in equilibrium chapter you will deal with the concentration of various species in solutions. And you need to understand why you neglect the water, concentration, because it's a change in the water concentration that is negligible. Okay, and that's why you don't worry about the water, it's always in excess. Alright, so the change in concentration of water is negligible. So before the reaction and after the reaction, it's still going to be the same amount, nearly about same amount of water in there. So it doesn't make any difference. So you neglect it. Yeah. So weak base, you can see there are some. So we'll just take off the water molecules from there. You can see that the weak base is gray, and you can see there are still many basic molecules. There are some bases that reacts with water, and in this case you can see that I think I forgot to make a point. Let's go to weak acid for a second. So here, what is the if we say this is an acid, HA is the acid, then what do you call water? Is it a base or an acid or neutral? No, Asmita, I said, remember one of the previous class we said don't focus on individual particles, always focus on reactions. Chemistry is not about particles. I mean, yes, it is about particles. You need to know the inherent properties of the particles, but it is more about the reactions. Okay, Vina is, that is correct, it is amphoteric, but in this particular reaction, is it acid or base? In this particular reaction, is it acting as an acid or base? It is acting as a base. Yes, because you have an acid HA. Obviously, you are what do you react? Acid and base. You get salt and water, and that's what you get. Yeah, basically, this is a neutralization reaction. Yeah. Obviously, water is in large quantity, so we neglect it. But again, as I said, in this particular reaction. So if you just focus on reaction, not on how many particles are there, don't focus on the beaker. Yeah, just on this particular reaction at the bottom, you see that the water is acting as a base. All right. In this particular reaction, what is the role of acid? What is the role of water? That is correct, Vinay. Yeah. What is the role of water in this particular reaction? No, is it an acid or a base? That's what I'm asking. You have to take the reference from the previous question. Is it an acid or a base? Very good. Okay, so this is a base in this, sorry, this is an acid. Yeah, we have base reacts with acid. So in this particular, so H is donating proton to the base. Yes, H is so water is giving the proton to the base, and therefore water is acting as acid, and this is a base, and so you got conjugate acid and conjugate base. Okay. So if you do that, so obviously you can see that many of the, so you know, this is the reason why we say water is amphoteric. Why do we say water is amphoteric? Because it is neutral. Is that the reason why we say water is amphoteric? Is that the right definition of water being amphoteric? Why do we say water is amphoteric? Because it can act as what? Exactly. It can act as an acid or a base depending upon the reaction, depending upon the situation. Okay, that is the beauty of water. Yeah. Um, all right. So now we see that water. We see that the base has not accepted all the base molecules has not accepted ions, H plus ions from water, and so you don't have many hydroxide ions in this solution. Yeah, there are some hydroxide ion, but not a lot. So you should expect this to be a weakly basic solution. Okay, you can see that from the concentration. You can see that the hydroxide ion concentration is not a lot. Okay, and so it's 10 to the power minus 5, and so it's weakly basic. It should be weakly basic. Okay, so let's see if that is the case. Dip the pH and it's 9.5. Yes, it is weakly basic. If you try it with excuse me, oof, excuse me, if you try it with litmus paper, sorry, pH paper, and you check it, yeah, it's about 9 or 9.5. So we know according to pH meter it is 9.5, but you can also say 9 just to get a rough estimate of what the pH is. Okay. um, so this is obviously weakly basic. Another thing you can test is, another thing you can test is if the solution is conductive or not. You can test if for both the so this would going to be your homework. Check the conductivity of all these solutions and compare the effect of conductance. Excuse me. Suddenly my cold came up. All right, let's do the reset. Bloody hell. Let's click on strong base. Okay, and this is a strong base, something like sodium hydroxide. Yeah, sodium hydroxide. In the previous case, weak base would be an example here, like ammonia. Yeah, ammonia is a weak base. It takes proton from water and gives you NH4 plus ions and OH minus ions. Yeah, so this is a weak example of weak base. Strong base, something like sodium ion, that is an ionic compound that dissociates completely in water. Okay. um, Obviously you don't see any gray particles in there. That's the reason is because all the sodium hydroxide or whatever the base it is, ionic base, has been completely dissociated. Okay. You see that hydroxide ion concentration is much more in this solution. You can see that from equilibrium concentration that the sodium hydroxide or base concentration is negligible, whereas OH minus ion concentration is very high. Okay, very high concentration. This should be a strongly basic solution. We have not shown here the concentration of water, but it's going to be there. It's going to be the same as previous example. Okay, the large amount of water is going to be there. Okay, so we dip the pH meter and see how much is the pH. What do you think? What is going to be the pH of this solution? Okay, let's first check it with the pH meter, a pH paper. See, it's a pH paper is basically a mixture of different indicators. Yeah, different indicators that change color at different pH. Remember, we talked about indicators in the previous example, Vinay. Yeah, it's a mixture of different indicators. They change color at different pH of the solution. That's what it is. Okay. So, okay, seems like you guys are right, and here we go. It is about 13, yeah, or 12 to 13, or about 13, 13 and a half, something like that, in that range. Yeah, and we can get an accurate pH reading by dipping it, and it's about 12. Oops, it's about 12. All right. So yes, we so so the dissociation of strong base is much more, dissociation of strong acid is much more, dissociation of weak acid is less, dissociation of weak base is less. Okay, and that determines the pH of the solution. Is that clear? Okay, let's try. Click on the custom solution tab. Okay, this is second lab, and let me see if I remember the directions. Alright, so here we have same setup, but now we can change the concentration. We can change different strengths of acid, different strengths of base. We can change. So the thing we can choose is, wanna make an acid solution or base solution. Okay, we can also change the concentration. There are few ways you can change the concentration, and you can also choose what type of acid or base you want. You want a strong base or a weak base, or strong acid or weak acid. Okay, so the bunch of different settings. These settings are exactly identical to the previous tab. Yeah, they are exactly identical. All right, so now let's choose acid first. Okay. it uh, it does react. Yeah, you don't have to dip the entire paper. I dipped it. Here's I dipped the entire paper because uh, I cannot turn the paper. Yeah, so how I'm gonna match the color, yeah, if I don't dip it entirely. So let's do it. Reset, and uh, yeah, and so let's say if I don't dip it entirely, how I'm gonna match the color. Yeah, so it's difficult. So if I dip it completely, then you can match the color. That's the reason why I dipped it completely. You don't have to dip it completely, just the tip a little bit of the so that the mixture of the indicator spread all over the paper in equal quantity. Okay, it's not like they are in different concentration at different places. Okay. Alright, so let's click on acid. So we're gonna use acid. Yeah, we're gonna change the concentration to 0.1. So I'm just gonna change that 0 to 0.1, and you should see that the concentration, what I want you to observe is what happens in this flask. Okay, you should see that the molecules, you should be able to see more of blue and orange molecules. Yeah, because we're increasing the concentration, should be more of these particles in there. Yeah, and so that's what you see, more of the particles in there. We simply increase the concentration, the strength of the acid is still same. Yeah, um, now okay, let me see if because in this particular lab you need to have a specific settings, otherwise you don't get particular readings. Yeah, that's the issue with this. Let me check with my notes. Hold on a second. Okay, so obviously the concentration, this is a weak acid. Yeah, so we'll reduce the strength to the weakest. Yeah, so now we'll reduce the strength to the weakest, and you can see that it's a very weak acid. Okay, it is a very weak acid. It is all. So if you change it to strong, you don't get that kind of setting. Yeah, so you can't change the strength of the strong acid or strong base. But if it is a weak, then you can change the strength. You can make it a strongly weak acid or weakly weak acid. Yeah, so this is to the weakest. Yeah, this is the weakest, very weak acid, and you can see that the dissociation is very little. Very few acid molecules are dissociated. Yeah, as shown in the previous. We've done this lab on the previous session. So previously, previous lab. It's exactly same lab. The only difference is now we're using a different setup. Yeah. Um, 1 second. Okay. Nothing important. Alright, so now let's check the pH of the solution. Okay, we should get slightly acidic pH, which is going to be around, I guess, 4 5, something like that, and yeah, it get around 5.5. okay, so we'll keep it pH meter dipped in. Okay, and what we'll do is we'll increase the strength of the acid. Okay, and what do you think should happen if we increase the strength of the acid? Should the pH go down or pH go up? Okay, very good. It should go down, and so let's when we increase the strength of an acid, we remember that we are keeping the concentration same. What that means is that we are using a different acid. We increase the strength. You cannot increase the strength of the same acid. Yeah, but if you change the acid to something different, if you have, let's imagine in a lab you're working like you have 5 different acids, same concentration, but in increasing strength. Yeah, that's the way it's going to look. Yeah, and so if you increase the strength, you can see that more of the gray particles dissociate. Obviously, you can see the pH goes down. Yeah, again, if you increase, pH goes down. If you take it all the way to the strongly pH stronger side, you see that the pH is 1. Okay, so many of the, you can still see some of the gray particles, because why? This is a weak acid. Yeah, you still see some of the gray particles, but many of the acid particles are dissociated, and so you see that this is a strongly acidic condition. Okay, you can't, Rohan, that's what I'm saying. You need to change the acid. Yeah, in this experiment we can, but you can't. You can change the dissociation by changing the medium, but if you change the medium, you may also change the pH. So the only way you can do it is by choosing a different acid. Okay, you can change the concentration, but here we are keeping the concentration same. Yeah, we are not changing the concentration. Yeah, in the next part we'll change the concentration. Yeah, so let's keep the concentration. So let's do the reset. Okay, so we still have control at base. Now we change the concentration of initial concentration to 0.1. Okay, we set the control to the weakest. Okay, so now we have a weak base, very weak base. Okay, now in yeah, so in this reaction, the gray molecules are base. Okay, the blue molecules are hydroxide ions, and the orange molecules are BH plus, basically the conjugate acid of the base. Okay, um, so you can see that not many molecules are dissociated. Essentially, we already know that. Now if we change change the strength of the base, if we make if we let's say if we replace this particular weak base with a different stronger base, what is going to happen if we keep doing that for a bunch of different times? What is going to happen to the pH? So let's first check the pH. What is the pH of the solution? So pH is about 8.5. This is a weak base solution. Yeah, what should happen to the pH? If we increase the strength of the base, pH will increase. That is correct. So let's see that. Yeah, and as you do that, you can see that more of the molecules start to dissociate. You can see, you can see clearly that more of the gray particles start to disappear, more of orange and blue particles starts to come up, because now we are making the base stronger. Yeah, we're replacing the weak base with a stronger base, and so the gray particles are dissociated, and at the strongest position you're gonna base as 13, and you can see most of the base particles are in ionic state, okay, as converted into conjugate acid, and you can see that blue particles are in large in number. Okay, similarly we can test it with equilibrium concentration. What is, so you can, when you change the strength of the base, yeah, again we just wanted to get that clear, that we are not changing the concentration. In practical life you can do that. You have to replace the base, you have to make a different solution with a stronger base, okay, and so that's the way you do it. So if we change the concentration, make the base stronger base, we will see that this should go down. Yeah, the gray bar should go down, the orange bar and the blue bar should equally come up, okay, and so that's what you see. So if you go, yes, initially you see that the concentration of the base does not decrease by a lot. The reason is because it is still in excess, it is still in large quantity. Yeah, you can see the concentration is still significantly large. 0.1 is a large quantity. Yeah, so the concentration of the base initially does not decrease as much. Yeah, but the concentration, since these are in very small quantity, their concentration, any change in their concentration, any increase or decrease in the concentration which is already in small quantity, there should be a large change in the resulting concentration. Clear? Because remember that logarithmic scale, yeah, that's the case, because they are already in such a small quantity that you change the concentration, they immediately double or triple, or they go, there is a significant increase in their concentration. Okay, but if you're saying let's say 100 particles of base changes to hydroxide ion, okay, if let's say 100 particles of, so there is not going to be any change in the base concentration, but there is definitely going to be change in the hydroxide ion concentration, okay, or conjugate acid of the base concentration. So initially you will see that the base concentration remains same, but conjugate acid, so the purple the orange and the blue bar, you will see that changes. Okay, you can see that these are changing. Yeah, and then at certain point you'll see that now you'll see that there is a when the base concentration decreases to a level, then suddenly there is a decrease in base concentration. Okay, and you'll see that there is a significant decrease in base concentration. The effect is again same. If it is in small quantity and if you decrease by half, there is a huge if you take out, let's say 1 million particles from it, it's going to be a huge change in the concentration. But if it's a large quantity, 1 million is not going to be a big difference. For example, if Bill Gates donates $100,000 to somebody, it's not going to make any difference to Bill Gates. Yeah, he's still going to be a rich guy, but ordinary average guy starts to donate $100,000, that's going to be a big difference. That's his income for many years. Actually, many people actually make $20,000-$30,000 a year. So that's 3-4 years of income for a guy. For Bill Gates, is not going to make much difference. Yes, is that difference clear? Okay, Vinay, I'll answer your questions later on towards the end, after the lab. Yeah. All right. So that is the lab for that is basically one lab for this. Um, Now let's reset this again. All right. So we come back to the custom lab tab. Um, we have okay. Let me hold on a second. Alright, so let's convert it into base. The concentration of initial concentration to be 0.001 moles per liter. Yeah, so we decrease the concentration in this particular yes, the lowest concentration. Set the base strength to strongest. Okay, it is still at weak, so let's just make it strong base, I guess. Yeah, and show the pH meter. So pH meter is up. I'm trying to read instructions from my cell phone, which is bit difficult. Yeah. Again, as I said, you need to follow specific instructions that are given in the notes, otherwise you don't get the same readings. Yeah, so make sure that you do, when you change the concentration, change it by typing it here, not by moving the slider. Yeah, usually don't work. Okay, so now what we'll do is we'll increase the concentration. So let's deep the pH. Okay, so the pH is 11. Yeah, remember that this is a base, this is a strong base, but the concentration is low. Yeah, if we, what do you think is going to happen if we increase the concentration? pH should increase. Correct, pH should increase. Yeah, if we increase the concentration by 10 times, what do you think is going to be the increase in pH? There should be a 10 times increase in pH as well. Yeah, if we increase the concentration of the solution by 10 times, what should be the increase in pH? Exactly, very good guys. There should be an increase in concentration by 1. Remember, log to the base 10. Remember that pH equation, that's how we calculate. So if you increase the concentration of anything by 10, the pH will increase by 1. Okay, and so let's do that, and we increase, and there you go, you got a pH of 12. Yeah, do the same again, you increase the concentration of this by 10 times, so we'll make it 0.1, and you got pH of 13. Okay, now let's make it 1. Okay, let's make the concentration to be a very strong and make it 1 mole per liter. Okay, and you see that the pH is 14. Okay, and that's basically your pH scale. That's the end of your pH scale. You can actually add more base, you can increase the concentration, but the pH you can increase by 10 times, and but the pH is not going to increase significantly. Yeah, it's probably going to increase by 4.2, 4.3, so on and so forth. But it's not going to increase as much. That's because after a while, we talked about it in the class, Anika. I think you said, I suggest you see the recording. That's because the scale is log scale. Okay, it does not, it is not a linear scale. Okay. All right. So So that's basically our acid base solutions lab. Now I'll do one titration lab, so I'll close this one. If you have any questions on this one, you can hold it till the end and I'll answer to that. Okay, so this is okay, that is correct. All right, so let's start with our acid-base solutions lab. This is a titration. This is a virtual titration. You can actually do the titration virtually in the similar way we did titration, or you do titration in your labs. Exactly the same thing. The only thing is you can redo this as many times as you want because there is no wastage here. Okay. So you got a bunch of things. You can different chemicals, you can take water, whatever different chemicals. You also have indicators here in a bunch of different indicators. If you click on the cabinet, these are cabinets, yeah. So click on different cabinets, you can get different indicators. Solid, conjugate bases, weak acids, yeah. If you can take, you can also take strong acids and strong bases. So you can take different things from these cabinets. Okay, pretty much all the chemicals that you find in general chemistry lab. What's a titration? Titration, you haven't done titration yet, guys? No? Man, what do they teach these days in the school, man? Okay, somebody has. Alright, titration is, remember that we talked about acid base reaction. Okay, what happens when you react an acid with a base? What do you get? If you react NaCl plus NaOH, what do you get? You get salt, and or you get NaCl and H2O. Yeah, if you react NaOH and HCl, you get salt and water. Can you use that for any practical use? Can you use it to, what is the use of that? You know, why do you have why do you even learn that? Well, the titration is a procedure where you can determine the concentration of different substances. For example, let's say you know, in laboratory you bought a chemical, yeah, you bought a chemical and you want to know, or you found a chemical in the lab, and based upon the preliminary tests you determine that it is an acid. Okay, it is an acid. You want to know what is the strength of that acid, what is the concentration of that acid. Okay, and to determine that, you would do a titration. You take a concentration of a base, you take a base of which you already know the concentration. Okay, and you titrate the acid with the base. You already know the concentration of the base. Okay, you don't know the concentration of the acid. You know what acid it is, but you don't know what is the concentration. Yeah, so you titrate it against the base, and you determine from the calculations, from the readings you do, you determine what is the concentration of acid. Okay, very simple, nothing complicated. These are different things you need for the lab. We're going to use very simple titration procedure. This is different equipments you need. Bunsen burners. These are the glasswares for the lab you need. Okay, okay, so different yes, exactly. So you can answer your lab your quiz question. You had the questions on in your lab, in your quiz based on these, but you know, those questions were basically theoretical questions. You can also do that, you find out practically. Okay, and this is how you do it if you want to know the concentration of different things. Alright, so what we're gonna need, this is the drawer, okay, from which you can take different glasswares. Here, oops, sorry, okay, I'm gonna delete that. This is solutions and strength, and at the bottom you have a pH meter. You also get the concentration of different things that is in this bracket. Okay, whatever chemicals we take, it will give you the concentration of different things. All right, so let's take beaker. So we take, first thing we'll do is we'll take an acid. Okay, so we take a strong acid. So we take click on this cabinet, we take 1 molar strong acid, 1 molar HCl. So simply double click on this, okay, and now you got, this is your workbench basically. So this is a workbench, yeah. You can see that it says first workbench, and so you have an acid on your workbench, okay. The concentration is 1 molar. It's a 1 molar HCl solution. That means you have this is how much is in there, okay. You got 100 ml of solution, okay. The strength is 1 molar. So if you had 1 liter, you would have 1 molar, 1 moles of HCl. Can you tell me how many moles of HCl is going to be in 100 ml of this solution? Exactly, yeah. 0.1 moles of solution, 0.1 moles in 100 ml. That makes 1 molar solution. Alright, so we take from the flask section, or from the glassware section, we take 250 ml of Erlenmeyer flask, okay. Conical flask and Erlenmeyer flask are interchangeable words. These are all same basically. We just called Erlenmeyer flask is a more scientific name. Conical flask is because of the shape of this. Okay, so what we do is we take this flask, yeah, and you can check the pH. You can see that if you click on this particular flask, yeah, you can see the concentration of H plus. It is 1 into 10 to the power 0, yeah. That means it is 1 molar solution, okay. That's 1 moles of so is in there. This is concentration. Hydroxide ion concentration is very little, 1 into 10 to the power minus 14. If you multiply that, what do you get? You get ionic product of water. Yes, 1 into 10 to the power minus 14. That's the product you get. That's the ionic product of water, okay. If you calculate the pH using okay, 1 second, where is it? Where did it go? Alright, if you calculate the pH using this concentration, you will get that the pH is 0, okay. Now we take this flask and just put it on this flask, and now you can pour the liquid, yeah. Whatever is in this flask, you can pour it on in this flask. So let's pour 25 milliliter of HCl solution, okay. So simply enter 25 in this flask, and you can either click pour or just enter, yeah, and that's it. So you can see that in this flask now you have 75 milliliter. That means you have already poured 25 milliliter into this flask, okay. You don't need this flask anymore, so simply right click it and remove from the workbench, okay. You don't need that anymore. So now we have Erlenmeyer flask, and you have 25 milliliters of HCl solution. You know the strength of it. It is 1 molar solution. You can see it, okay. The pH is still 0. Alright, now let's put it here at the bottom somewhere. Now let's take a strong base, okay, from the chemical section, and we take 1 molar sodium hydroxide. From a double click it, you got 1 molar, okay. Now we need a burette, okay. So burette is here. You just click on 50 ml burette, okay, right there, and just click on it, and you got a burette, okay. So these are the things we need. Alright, so let's take the burette, put it here, and take the NaOH solution. You can see that it is a 50 ml burette, so that is the maximum amount of solution you can add in this burette. So usually base usually goes on the burette, acid goes in the Erlenmeyer flask. You can interchange it, but you know, it is better if you do it like this, okay, because the reaction is exothermic. it is better if you add sodium hydroxide into acid rather than other way around. Yeah, it is also if the acid is strong, it is more likely that you may spill it while adding it into the burette, and that is more harmful than if you spill sodium hydroxide. Okay, so it is much more safer that you add sodium hydroxide into the burette. So let's bring it over here, release it, and since we need, we don't need 50 ml, but we'll fill the burette to the mark. Okay, so we'll add 50 ml. Yeah, so you can see that 50, and either you can click on pour or enter. I just usually enter, and you got 50 ml. Okay, again you're done with sodium hydroxide. You can remove it. Yeah, you can see that there is a 50 ml of liquid. You also know the strength of the hydroxide of this solution. It is 1 molar solution. Okay, you have 50 ml of 1 molar solution in this puree. So in practical life, you would not know the strength of the acid or strength of the base. Okay, one of those things, but you can calculate based upon the calculation. Okay, how much of acid is consumed or how much of base is consumed based upon what type of acid or base you have. Okay, now let's we can do the titration, but how would we know that the neutralization reaction has been done? We can add base to the acid. We can add base to the acid, and at some point the base will neutralize all the acid in this flask. Yeah, but how would we know that the neutralization reaction has been done? Very good. We cannot use pH. We can use pH paper, but it's not practical. As I said, you can dip it in and take it out all the time. That's also going to you're also going to lose the liquid if you use pH paper or pH meter. You can use pH meter, electronic digital pH meters. But the classical way of doing things is you use indicator. Again, you can use litmus papers or pH papers, but it's not practical. Okay, when you do the lab, you'll see that it is not practical if you use pH paper. You don't get exact reading. Okay, the reading is usually off if you use a pH paper or litmus paper. That's because these are visual indicators, and they don't you're not sure if the end point is reached. If let's say you're using a pH paper, okay, so you can see that there is a range where the neutral color is pretty much same. Yeah, but you can use an indicator. Let's say you use a phenolphthalein indicator. It's a classical. What is the peculiarity of phenolphthalein indicator? Do you guys remember from the previous session? What is the peculiarity? What is the range of turns pink with bases, but which pH range actually? Above 7, above 9, above 10? Above 7, correct. So as far as the solution is not neutral or acidic, the phenolphthalein will be pink. Is that clear? Above 7, yeah, as far as the solution is not neutral or acidic, phenolphthalein is going to be pink. Alright, so you can see that it is colorless right now because it's just a phenolphthalein, and you can add it over here, and we want to add small quantity. Remember that phenolphthalein is also can interfere with your results, so you want to add very little quantity of acid. Remember that it also has H plus, and if you click on this one, you can see that it also has H plus and OH minus ions in there. Yeah, it's slightly on the acidic side, and you want to make sure that it does not interfere with your titration. So you want to add small quantity. Usually in lab, you will be adding about 3 or 4 drops of phenolphthalein. Okay, usually 3 drops of phenolphthalein is enough. Okay, so what should happen? Well, nothing should happen. We should add 0.25 milliliter of solution. Yeah, 0.25. That's it. You can see that change. There is a slight change in the H plus minus and OH minus ions, but it's not significant change to show a change in the pH. Okay, so we're done with the phenolphthalein. We can take it out. Alright, now you can see, click on the unlimited flask. You can see the volume is 25.25. That means you have 25 ml of acid and 0.25 ml of phenolphthalein indicator in that. Alright, you can also calculate the ionic product of water. It's still going to be the same. It's not going to change. The ionic product of water is always same. Alright, and since the solution is acidic, the phenolphthalein has not changed the color. Yes, it is. So if we add base, okay, so we add base. So this is the setup. You have burette now, and you can slowly add base to the acid, and obviously if you add little base, a small neutralization reaction will take place. Yeah, small amount of acid will get neutralized. Let's say you add 1 ml of base. Okay, some amount of acid will get neutralized. That is going to be decided by the strength of the acid and base, okay, and the concentration of acid and base. So some amount of acid is going to be neutralized, and that will keep on happening as far as you keep on adding base to this flask. At one point you should neutralize all the acid, okay, if you keep on adding small amount of base in intervals. Okay, so you should be able to see the neutral point. Okay, and after the neutral point, when you so it's still going to be colorless. You won't see any change in the color. You will see that there is a appearance of the pink color, but it will keep on disappearing. Okay, the pink color should persist for some amount of time for be able to say that the neutralization reaction is complete. But as soon as the neutralization reaction is done, as soon as the solution is neutral, you still see the solution is colorless, but the next drop of base you add into the flask should give you a color change from colorless to pink, and that is where the solution now has become basic. That means you have a slight excess of base in the solution that will change, that will make make phenolphthalein change the color to pink. That is your end point. Okay, is that clear, the theory part? Okay, that means, so let's say you don't know the concentration of acid. For example, just imagine you don't know the concentration of the acid. I think, I think because we already know the concentration of the acid, let's say the concentration of the acid is 1 molar solution. Okay, the concentration of the base is 1 molar. Can you tell me, so this is 25 ml of 1 molar solution, the acid, yes, 25 ml of 1 molar acid solution. Can you tell me how much of base we're going to require for this neutralization? How many mLs of base we're going to require? This was, I think, one of the questions. We know the strength of the acid. Yes, we know that it is 1 molar solution. We know the quantity of it. We know that it is 25 milliliter of 1 molar acid solution. Yeah, we know the strength of the base. It is 1 molar sodium hydroxide solution. Can you tell me how much is the quantity of the base we're gonna require for this titration? You have solved the questions in the quiz based on the similar type of questions in the quiz. This is 1 molar HCl solution. Oops, no, this is 1 molar HCl solution. Oh, not like that. This is 1 molar sodium hydroxide solution, and we can use this information. We know the quantity, we know the strength. We can use this information to calculate anything we want. If we can calculate the strength, or you can calculate the quantity. Okay, so in the meantime you are working on that. I'll proceed with the titration. I'll keep on adding a little bit of base at into the solution. So let's say I'll add 0.5 milliliters of base. Okay, a small quantity at a time. We'll add 0.5 milliliter of base into the Erlenmeyer flask, into the acid. You can see that the quantity is 1. So this is the marking is 1 on the top. Yeah, it should decrease by 0.5. You should also be able to see that the quantity of liquid in the Erlenmeyer flask should also increase by 0.5. Okay, you should be able to see some changes in the H plus and OH minus ions in the solution. You should be able to see some change in the pH, but it's not going to be noticeable. Alright, so let's add 0.5, enter, and so we added 0.5 milliliter. You can see that the solution in the Erlenmeyer flask is okay. We'll see if that is correct. So the solution in the flask is 25.75 milliliter. Yeah, you should be able to see that there was a slight change in temperature also. Yeah, now it is going down. Yeah, the reason is because the reaction is exothermic. It will increase the temperature. You can see the hydroxide ion concentration has changed, has decreased a little bit. Hydroxide ion concentration has increased a little bit, but the ionic product has remained same. Okay, you can see there is a slight increase, very small increase in pH, 0.02. That's pretty much zero from our standpoint, but so that's the slight change in pH. Okay, so we'll keep on adding a little bit. That is correct, Anika. Alright, keep on adding a little bit, and so you can see that changes. There's pH changes and there's a concentration changes in this excuse me in this lab. Okay, so we'll keep on adding until so we'll have to add lot of liquid. You can see that there is the pH is changing. We have added almost about 11 milliliter of, so now you have 39 milliliter. Oh, so why is that going up? I don't know. Okay, so you have 36 milliliters. So we started with 25, so we have added about 11 ml of sodium hydroxide in the flask. Okay, you can see the temperature went up. See the pH increased, but not by much. There is still the decrease in hydroxide ion H plus ion concentration. There is increase in H plus ion concentration, but you can see this is the blue bar. The first blue bar is the H plus ion concentration, and this green bar is hydroxide ion concentration. Okay, you don't have to pay attention to the other bars, just the first two bars pay attention. Okay, so add 0.5 again, and you can see that the same changes is happening. Yeah, keep on happening. Will probably need to be close to about 49 ml in total. You can see the total quantity of liquid in the Erlenmeyer flask. Yeah, it is increasing. You can see the hydroxide and H plus ion concentrations are changing, but not by much, and therefore the pH is not changing by much. Okay, 45, 46, 47, 48, 49. Okay, so now you can see the pH is 1.69. yeah, this is mildly acidic solution. You can see there is a significant decrease in H plus ion concentration. There is a significant increase in hydroxide ion concentration. Okay, now let's see if we add a little bit more of base. It became 2. Okay, so now you have 49.75. so let's add one more, and you should be able to see a significant change in the equilibrium. You should see that much of the hydroxide ion should go, and there should be an increase in, so H plus and OH minus ion should match. Yeah, so that's what is happening. H plus ions are decreasing, hydrogen ion concentration is increasing and here it is the end point, this is the neutral point. You can see that the pH is about 7. You see the H plus and OH minus ions are there. pH about 2 is not a strong pH. Yeah, it's yeah, you know, pH 1 is a strong pH, a strongly acidic solution. pH 2 is you can say medium strong pH, something like that. Alright, so you can see that the hydroxide ion and OH ion concentration are equal. Yeah, this is a neutral solution. Yes, and you can see that the phenolphthalein does not change color in neutral solution. It is still colorless. Okay, so when you're doing it in the lab, you won't know if you see the neutral, if the endpoint has been reached. Okay, there is no way you will know that the endpoint has been reached. But as soon as you pass that neutral point, as soon as you pass the pH 7, you'll immediately know. Okay, so we add one more 0.5 milliliter of solution into the base, and you should see that there should be a huge increase in pH. You should see that the hydroxide ion concentration, this green bar, should go up and this blue bar should go down, and you should see the most important point is that the solution changes color. Okay, and there you go, this is a pink solution. All the changes has taken place. The pH is now 12. The hydroxide ion concentration is significantly more than H plus ion concentration, and the solution is now pink. Okay, remember that we reach the end point. This is called as end point because this is visual to us, but the titration was already done before that. Okay, but we had to add a little bit extra of sodium hydroxide solution to see the end point. Yeah, and this is going to be your final reading. This is, you know, so if you calculate, this is going to be about 25 milliliters of NaOH solution that you added. Okay, you can see that the final solution is 50.75. Yeah, we added extra 0.5 at the end, and we also added 0.25 of phenolphthalein at the beginning. Yeah, so that's 0.75. So essentially we added essentially we added 25 milliliter of sodium hydroxide solution into the flask. Okay, so this is how the titrations are done. You will do that in the lab. If you haven't, you know, you can go and it's interesting if you do it. There are different indicators will give you different colors, but they also have different range. Okay, try this. If you have any issues with this, let me know. This is, again, you can do this online in the browser. You don't need to download this this app, but you do need Java for it, so make sure that your Java is updated. You can download it. I have downloaded because, you know, it's much better if you download it because you're not dependent on internet connection. But it's a large application. In fact, you can download it and you can use it if you want. Yeah, it's freely available. The link is posted on the Learning Center. So when you click on the link, you will go to their website. This is Iridium Chemistry Lab, and you'll go to their website. You will see that this is going to take a little bit of time to load, but once it loads, it will run fine. At the bottom of the table, at the bottom of this page, you're going to have a download link. You can download it. It's significantly large. I think it's about 150 MBs of file for this one. So you can do pretty much all types of titration. You can do you know, strong acid, strong base, weak acid, strong base, weak base, strong acid, so on and so forth. So again, there are different types of titration. It will help you understand how the titrations are done. So when you, in the next year, when you learn about titrations, okay, when you learn about equilibrium, you will have much better idea about you know, acid-base chemistry, or acids and bases, or equilibrium. Anika, that is correct. Yeah, 250 is the size of the flask. Yeah, not the volume of liquid. Okay, so this is the end of the lab. Again, if you have any issues, let me know. I'm gonna stop the screen share now.